Awesome, perfect. We can see it. Well, the floor is yours. Thank you, Guillaume.
Thank you, Thomas. Thank you, everyone, for coming here. I'm very happy to show you today some of a part of my work. So, as you said, Thomas, I will talk about the Runaway greenhouse effect and about climate modeling in general. So, as you know, I guess, since many years, we discovered a lot of planets. I saw recently we passed by the 5,200 planets. So it's really cool to have a lot of targets to study. And thanks to a large variety of techniques, we can observe a large variety of environments and large variety of parameters for these planets. As you can see on this mass period diagram of the known exoplanets. If we check on this diagram, the Earth is around there, but yeah, there is no exoplanets like the Earth in terms of mass and period, which is quite sad for me because I study mainly the Earth-like planets and the small rocky planets. But if we look at the equivalent diagram with planetary radius and insolation, we have some candidates like similar to the Earth. Of course, there is the famous TRAPPIST-1 system, but there is also other example, for example, Ross 128b and other planets. So I during my PhD, I really focus on these kind of planets, and I try to model the climate of potential climate of those planets using different climate models. So I say there is a large variety of planets we can observe, and if we talk about habitability, the only example is the Earth, of course, for life. But even on the Earth, the life can survive and can evolve in a large variety of conditions in terms of temperature, pressure, salinity, and so on. If we resume this very complex question of habitability with in simple words, we can extract three important parameters to search for life. First, we need materials, so simple molecules, atoms. We need energy. And we need liquid water, because liquid water is the best solvent we can have, and it's also quite abundant in the universe. So for my PhD, I focus mainly on liquid water because thanks to the models we have, we can try to estimate and we can search for potential climates which allow liquid water at the surface of the planet in this big picture of habitability. And yeah, when we discuss with biologists, they say that the liquid water is a sine qua non condition for the emergence of life, for the reasons I mentioned before. So if we want to find liquid water at the surface of a planet, we need to estimate the temperature of those planets. If we assume that the equilibrium temperature is an equality between the absorbed flux and the thermal emission, we need to estimate the thermal emission of those planets. It's quite easy if the planet is only a rocky body without any atmosphere, but when there is an atmosphere around the planet, this question of the thermal emission is much more complex. So yeah, we need there is a strong interest to be able to accurately estimate the thermal emission of the planets with an atmosphere. To go a little bit more in the detail of this question of the thermal emission, we can consider a small rocky exoplanet with an Earth-like ocean which move towards the star. As the stellar flux increase, the temperature of the planet increase, then the evaporation increase, then the greenhouse effect increase, and the temperature increase, etc., etc. This positive feedback is named the runaway greenhouse feedback. And because of that, and because of the strong greenhouse power of the water, at some point, when there is enough water in the atmosphere, the bottom part of this atmosphere will be optically thick to the thermal emission, and the thermal emission curve function of the surface temperature will reach an asymptotic limit, as you can see on this figure. And because of that, the planet is not able to cool down anymore, and the temperature of the planet will increase continuously to reach thousands of degrees. So this limit is useful because if we take the definition of the equilibrium temperature I mentioned before, we can, thanks to this asymptotic limit, we can define the maximum absorbed flux accepted by the planet before falling into this runaway greenhouse. And thanks to this maximum absorbed flux, we can also define an inner limit for the habitable zone. So there is a lot of study working with this definition. You can see here an example of the evolution of the position of the habitable zone, function of the luminosity of the star, and the temperature of the star. And beyond this asymptotic limit, when the planet is hot enough, the planet starts to emit in the visible, for which the vapor is optically thin. That's why at the end, the thermal emission curve increase again. So this we have three states on this curve. Before the runaway greenhouse, there is temperate, habitable, stable states. There is this unstable states of the runaway greenhouse, and at the end, we obtain a very hot planet with new stable states, post-runaway states. So this asymptotic transition split the population of rocky planets in two, because when the entire ocean is evaporated in the atmosphere, the planet is super hot and super puffed. You can see on this diagram here an example of the temperature profile before the runaway and beyond the runaway. So it's really interesting to study this transition to understand correctly this dichotomy between temperate and steam planets. There is few study for the pre-runaway and the post-runaway states, but this transition itself is not super well understood because there is no study with a very complex climate model for this. This runaway greenhouse is also interesting for the Earth because the Earth's insolation corresponds to an equilibrium temperature quite close to this transition. So regarding the context of the climate change, it may be interesting to estimate what is, to understand this transition, and also to estimate what is how exactly is the onset of this runaway transition, and in other words, how far are we to this catastrophic transition? Because, for example, as you can see here, if there is an overshoot of this asymptotic limit, for example, with the green curve, the security gap is kind of bigger than if there is an undershoot with this blue curve. So yeah, it's quite interesting to know that, I guess. So to study this question, we can first use a very simple 1D model. It's pretty fast and pretty useful because those models provide us interesting quantity. For example, the temperature profile, the mixing ratio in the atmosphere, and so on. So with this model, we can first estimate the Simpson-Nakajima limit, this asymptotic limit of the runaway greenhouse. But we can also add other gases, for example, nitrogen. And nitrogen is funny because it's radiatively inactive. But when you add nitrogen in this atmosphere, as you can see, there is a strong modification of the thermal emission, even with a low nitrogen pressure. And if you increase the quantity of nitrogen, the thermal emission curve is modified more efficiently. And the interesting point here is that with nitrogen, the thermal emission curve overshoots the Simpson-Nakajima limit. So there is different interpretations of that. But the main point is that if we explain it as in simple words, if the thermal emission is higher, then the capacity of the planet to cool down is higher, and then the inner limits of the habitable zone is closer to the star. So this effect of the radiatively inactive nitrogen is quite interesting. We studied also the effect of the addition of CO2 on this thermal emission curve. It's the dotted lines here for similar quantities. And of course, because of the strong absorption power of CO2, there is no overshoot of the thermal emission, but the overshoot of this asymptotic limit, but the thermal emission curve is strongly modified by the absorption of CO2 alone. So if we try to compare the effect of CO2 and the effect of nitrogen, as I said, if we had nitrogen in the atmosphere, the inner limit of the habitable zone is closer to the star. But there is no modification of the maximum of the thermal emission by adding CO2. So the position of the inner limit of the habitable zone with or without CO2 is the same. But if we look at the last equilibrium temperature we can reach in these three scenarios, here is the maximum temperature for the pure vapor case. When there is nitrogen, this last equilibrium temperature is a little bit higher. So that means the inner for this planet, the inner limit of the habitable zone is closer to the star, and the temperature is a little bit higher. And for CO2, there is no modification of the position of the habitable zone, but the temperature is much more higher than for pure vapor. So if we look at nitrogen, and if we look at the different papers there is in the literature, we can see that there is a very broad estimate. The estimations of the thermal emission for this atmosphere are multiples, and there is no real accordance between the studies. So we did a lot of sensitivity tests to try to explain these differences and maybe provide some advice regarding the important processes we should take into account to correctly estimate this transition, this onset of the Runaway greenhouse. I wanted to highlight one process. So the important points for the onset of this Runaway greenhouse is the fact that there is a transition of the dominant spacing. So at low temperature, all the water is condensed at the surface, and for the case with nitrogen, the atmosphere is nitrogen dominated. And at high temperature, at 500 K, there is a lot of evaporation, and the atmosphere is water dominated. So this transition from nitrogen dominated to water dominated induces a transition of the atmospheric structure. But there is also a transition of the broadening spacing. That means at low temperature, the water lines are broadened mainly by nitrogen, because there is collisions between water and nitrogen due to the large number of nitrogen molecules. But at high temperature, when there is mainly water, the water lines are broadened by collision between water and water. And the broadening power of the water is much more efficient than the broadening power of the nitrogen. So if we neglect this transition, so if we assume that the water is broadened only by water, whatever the surface temperature and whatever the mixing ratio in the atmosphere, we obtain the red curve. So we overestimate the absorption and we underestimate the thermal emission, and we can miss completely this overshoot of the thermal emission. So yeah, we have to keep in mind that there is this transition of the dominant species, and then we can't neglect, for example, this broadening effect to accurately estimate the thermal emissions. So the conclusion of this of what I explained, and particularly this overshoot of the nitrogen, is that, as I said, the planet is able to cool down more efficiently. And for the Earth, there is the same conclusion, I would say, but as there is other gases, for example, CO2, CH4, the thermal emission curve is not the same, because CO2 is a strong absorber, so the thermal emission cannot reach that high values. But in this very simple model, 1D model, we neglect clouds and we don't have any advection. There is no dynamics. So as a second step, it's interesting to use a more complex model to see if these conclusions and these estimations of the thermal emission are true or inaccurate due to the assumption we do. So to do that, I use the GCM, the Generic-PCM model. It's the LMD, the model developed at the LMD, but the name changed. So yeah, it's a very complex model, and there is a lot of physical processes inside. First of all, the dynamical core to compute the global dynamics in the atmosphere. But there is also radiative transfer calculations. We account for condensation, raining, and so on. So we did the simulation with the same kind of atmosphere with water and nitrogen. And you can see on this figure the comparison between, in red, the 1D estimation of the thermal emission, and in cyan, the thermal emission for a simulation, for a cloud-free simulation. So as you can see, the maximum of the thermal emission is much higher in the 3D simulation. This one's explained a few years ago in 2013 by Jérémy Lecomte by the global dynamics. More precisely, the Atlas cells around the equator tend to reduce locally the relative humidity, and as there is less humidity, there is less absorption, and the thermal emission can be higher. If now we add we account for clouds in the simulation, we obtain the blue curve. So of course the thermal emission drops because there is this strong absorption of the clouds. But the interesting point here is that for stable states, so here at low temperature, the difference between the cloud-free thermal emission and the cloudy thermal emission is more or less constant, whatever the surface temperature. That means the cloud coverage is constant by increasing the surface temperature. But when we go in this runaway greenhouse, because of the strong evaporation, the cloud coverage will increase super quickly and super strongly, and the difference between the cloudy and the cloud-free simulation increase as well. So there is at the end two parts on this curve for the onset of the runaway greenhouse. So the first part here for stable states, temperate states before the runaway greenhouse, the dynamics is the key component to understand the evolution of the thermal emission. And this second part here in the runaway greenhouse transition, the clouds are the key process to understand the evolution of the climate and of the thermal emission. We did these simulations for different scenarios, with or without the Earth's continents, for different nitrogen pressures with a little bit of CO2. You can see here an overview of these results. And for me, an interesting point is that for similar quantities of nitrogen, I mean, for one bar of nitrogen, doesn't matter if there is continents or not, doesn't matter if there is a little bit of CO2. During the runaway greenhouse, the evolution is the same. And we can see that if we look more in detail in the evolution of the climate, when the clouds are dense enough, there is no more interaction between the thermal emission at the top of the atmosphere and what happens at the surface, or what are the minor components of the atmosphere. So for the rest of the presentation, I will just focus on one single simulation with water and 1 bar of nitrogen without CO2. Because of that, because the global evolution of the climate is the same. So you can see here a few interesting quantities. Here at low temperature for stable states, the first row, and the second one is during the runaway transition. So for temperate states, we can see that the vapor is mainly distributed around the equator. And we can see also these well-known plumes around the equator. And here the thermal emission is anti-correlated with the distribution of the vapor. But during the runaway transition, the cloud coverage increases strongly, as well as the quantity of vapor. And now the vapor is well distributed around the planet. And the thermal emission is anti-correlated with the cloud distribution. If we look a little bit more in detail on the evolution of the cloud coverage during this runaway greenhouse, you can see that as I said, the quantity of clouds increased strongly because of the strong evaporation. And at the beginning of the runaway greenhouse, there is a low tropospheric cloud deck, and at the end of the simulations, the clouds are more in the top part of the atmosphere. So this is super efficient to warm up the planet, because if the clouds are at the top of the atmosphere, you absorb more thermal emission than when the clouds are at the bottom of the atmosphere. If we look now on the latitude longitude distribution of the clouds, there is also another interesting pattern. Here for temperate states, this map is average at the subsolar point. So it's average over 1 year of latitude longitude at the subsolar point. And here for the temperate state, the clouds are kind of well distributed around the planet. But during the runaway, there is this dichotomy between a cloud-free day side and cloudy night side. And again, this particular pattern described in a very recent paper of Martin Turbet is super efficient to warm up the planet, because there is a very low albedo on the day side, and there is a strong greenhouse effect of the clouds on the night side. So, and yeah, it's also very nice for us to see the similar pattern during the runaway greenhouse at the beginning of the runaway greenhouse, and for post-runaway greenhouse states. So what Martin studied in this paper, we have exactly the same pattern, which make the simulations. We are more confident in what we do because of that. If we look at the distribution of the winds, for temperate states here, we see the two Adler cells around the equator. And during the runaway greenhouse, we see that these patterns evolve. At some point, there is no pattern at all. And we converge on a new global circulation with two cells around the equator, but all the dynamics is at the top of the atmosphere, because at the bottom part of the atmosphere is optically thick, and basically nothing happens anymore. And it's the same for the winds. We have the same pattern in my simulations and in the simulations of Martin at very high temperatures. About the winds, there is an interesting effect we saw. So the pattern I described is for the Earth with the continents. But if we remove the continents, if we assume a water world, basically, you can see that here we don't see these two Adler cells around the equator. Actually, they exist, but one of the two cells is bigger than the other, and it's non-usual to see that, but we investigated a little bit this, and actually it seems that because there is no continents, there is more evaporation, and there is more vapor in the atmosphere. And there is, because of the obliquity of the planet, there is a feedback, a water feedback, vapor feedback, and on one hemisphere, you increase the quantity of vapor, and then you increase the absorption because of that. And then you have these cells around, the equator, and you this circulation seems stable because of the feedback of the vapor. Yeah, well, it's not super important, but it's interesting to see that we have a different simulation, different circulation for the same temperate state, with or without continents. But by the way, at the end of the simulation, we always have this circulation at the top of the atmosphere, whatever what we assume at the surface. Yeah. So we, after this study of the onset of the runaway greenhouse with this evaporation phase, we tried to go deeper in the analysis, and we say okay, we don't see any moist stable state. We still try to understand why we don't have any moist states. I mean, any stable states at low temperature after this evaporation phase, because there is a few studies which claim this moist stable state, but we are not able to reproduce that with our model. And it's not super clear what are the physical processes behind this difference. So, well, we say we have this evaporation phase, but at some point the entire ocean will be evaporated. So we stopped the simulation, and we removed the ocean from the surface, and we keep all the parameters unchanged, and we let the system evolve to see what happens when the entire ocean evaporated. So we did that, and we observed a quick increase of the surface temperature, because the bottom parts of the atmosphere becomes dry, just because there is no addition of vapor from the bottom. So yeah, the bottom part of the atmosphere becomes super hot, and the surface temperature increase. And at some points, because of this increase of the surface temperature, you will re-evaporate the clouds from the bottom. So you reduce the quantity of clouds, and because of that, you modify the albedo, and at some point, the thermal emission increase again to reach a new stable state here at very high temperature. So This second part of the evolution is function of the quantity of vapor there is in the atmosphere. So that means the depends on the size of the initial reservoir. Yeah, this the pattern of these stable states we find at the end is exactly the same to the pattern observed by a previous study. So yeah, it's there are post-runaway states basically. So at the end, we have three parts. As I said at the very beginning, on this curve, we see habitable states, and by increasing step by step the insolation, we reach this runaway transition. And after an evaporation phase, when there is no ocean at the surface, we see this quick increase of the surface temperature to reach post-runaway states. So yeah, we are pretty happy of these simulations, because it's the first estimation of this entire transition with a complex GCM. Finally, we obtained two different population of planets. So the question is it possible to observe this difference or the difference between temperate planets and post-runaway planets? So we used a tool named the Pythmosphere and developed in Bordeaux in France. This tool is able to take output of GCMs to produce transmission spectra and transmittance map. So we did that for a few interesting points along this evolution. So at very low temperature for temperate states, you can see here front face vision of the planet with the core at the beginning, and the in color the transmittance of the atmosphere. So here what we see is that the atmosphere is super thin and not extended at all, basically what we have on the Earth. If we increase a little bit the surface temperature, but when we keep a temperate stable state, the atmosphere is a little bit bigger, but yeah, it's basically the same quantities we have. But after the evaporation phase, at the end of the evaporation phase, because there is a lot of vapor in the atmosphere and a lot of clouds, so the visible size of the atmosphere is, of course, largely bigger. And if you go during this transition phase, when there is no ocean remaining at the surface, we can see that the atmosphere is a little bit bigger because the planet is hotter, and it's even more visible when we increase strongly the surface temperature. So I'm not an expert of observation, but it's really interesting to see this difference visible of the visible size of the atmosphere from temperate states to post-runaway states. We tested also to produce some transmission spectra. So in transparency, you can see the transmission spectra of the cloud-free simulation, and the flat curves are, of course, the cloudy simulations. So same as just before, for different interesting points, we tried to estimate this transmission spectra. So the main simulation is an Earth-like planet around the Sun-like star. So of course it's not really observable. It's only a few ppm. But if we model a TRAPPIST-like planet with a TRAPPIST-like star, from few ppm we go to a few hundred of ppm. So this may be this is maybe observable. And also an interesting point is that, of course, it's flat because of the clouds, but for temperate states, we have these little bumps of the water Then during the evaporation phase, it's like hugely flat, but at higher temperature, we see again these little bumps because all the water, because of the super hot temperature, all the water is pushed at the top of the atmosphere, and also because the atmosphere is hotter, then it's easier to detect water. Well, so all of that to say that maybe it will be possible to with James Webb to distinguish these two populations. Let's see. So I will finish with a few conclusions about the results we have with the 1D model on these spectroscopic effects, important spectroscopic effects, and about this modelization of the runaway transition from temperate to post-runaway states. So yeah, thank you for your attention. If you have any question, please feel free to ask.
Thank you very much, Guillaume. That's a super interesting presentation. Yeah, do we have any questions? Yeah, Avi?
Yeah, really great talk, Guillaume.
Thank you.
My my video is a little messed up, but here I just try to switch that. So I was wondering if you had looked at thermal emissions, since you know, I think you're probably aware that obviously the LIFE mission is thinking about thermal emission from M-star planets, and we just published a paper with another mission concept that could examine temperatures of terrestrial and sub-Neptune planets for temperatures from 250 up to 700 Kelvin, and in thermal emission in the mid-infrared. And so it'd be really great to see what the predictions would be for thermal emission. As you said, the temperature, I mean, you already have the calculations done, but the contribution of clouds from the day side and other factors, especially phase curves, as a function of phase for a tidally locked planet, would be really exciting as well.
Yeah, sure. But yeah, you say it's for sub-Neptunes, right?
Terrestrial up to sub-Neptune. It depends on.
Okay.
Yeah.
Okay. Because for this runaway greenhouse effect, we absolutely need water. If there is no water, there is nothing like this. Yeah, I don't know all the missions, and I'm not an expert of that at all, as I said, but yeah, I know that there is a lot of instruments which will be able to maybe detect that. So it's very exciting to.
Yeah, I mean, I think the challenge you're seeing with transmission spectroscopy is very telling about what will, the challenges for James Webb will be for transmission spectroscopy. But the same challenge, emission spectroscopy does not have the same issues with cloud cover, or at quite the same level, and especially for for water and carbon dioxide and some of these major absorbers, you should be able to see these effects of the change in the cloud altitude, the water vapor burden in the atmosphere. All of these factors should produce really interesting, along with the thermal, as you say, with the change in temperature, thermal emissions should create very distinctive differences in the thermal emission spectrum, which should be much more detectable with upcoming missions. So something to think about.
Yeah, absolutely. Yeah, I really agree with Avi. If I can jump in, yeah, specifically as you're really looking to different phase and transition on this diagram that you have on the bottom left, yeah, it would be maybe great to see that, when you have like a stable state, temperate, transmission spectroscopy is great, and the more you evolve in temperature, then you see that you will have, would be much easier to detect spectral features going into the thermal emission after, and so you can have really this transition there of techniques, and
we with Emmeline, we tested briefly the detectability of this transition, but I try to finish the paper about that, but I hope a lot of people from the observation community will take that and try to see if it's useful or not, as you say. Yeah.
Yeah, the other thing is, even right now, we are just finishing the observations of the JWST of TRAPPIST-1c in emission at 15 microns to search for evidence of either a decrease in temperature expected for, a runaway atmosphere like this, or as carbon dioxide absorption at the 15 micron band. So that paper could come out next couple months, and I think
interesting.
great to have some predictions to compare.
Yeah,
So,
I really would like to see this paper. We are waiting actively for this.
yeah, the last data set just came in yesterday, so
okay, so it's very fresh.
We're working on it.
Cool.
But,
good to know that. Thank you.
Absolutely.
So yeah, Mike, I've seen you have written a comment question in the chat. Do you want to say it out loud?
Yeah, my voice is not so great. That's why I wrote in the chat. But it was a great talk, Guillaume. Unfortunately, I had a prior commitment, so I only saw the last 20 minutes. But I'm just curious. I've mentioned this to Martin before. Have you considered looking at these other atmospheres that are predicted from these outgassing models of Bauer and, of course, Gaillard, Scalé? Because some of them are showing that you might not get very much water vapor out at all in these early atmospheres. And it seems like that's a key component in all these very early scenarios because of these water clouds that are formed. And if you don't have those, or you have some other kinds of atmospheres, the thermal history of the atmosphere might be quite distinct, actually.
Yeah, true. If there is not enough vapor, actually, to initiate this runaway greenhouse effect, we don't need too much vapor. For example, here I tested 1 bar and 1.5 bar of weight of water. So we are quite far from the 270 bar we have on the Earth. But basically, if there is no water at all of this is absolutely not the same. There is no instable transition. So yeah, do you have an atmosphere, a kind of atmosphere in mind specifically, or is it general remark?
Yeah, no, I mean, I think some of the models are really interesting. They show like CO dominated atmospheres, or CO and CO2 dominated atmospheres, very small amounts of water, or even CH4 dominated atmospheres of all things, totally depending upon what the C to O ratio is, and the mantle redox state, or whatever you want to call the mantle back in that time. So I think the problem is the parameter space is very large still, and we don't really know what these primordial atmospheres look like. I think, not to take anything away from what you've done, I think what you've done is extremely important. And as Martin has seen me give talks about this like 3-4 years ago, someone has to do this. So I'm so glad that you all did it. But I think we need to look at some more parameter space to see what else is out there. And the other thing I caught at the end, and I apologize if you mentioned it before, but I think you were saying that some models are showing this cloud albedo feedback, but that your model had trouble producing that for these slow rotators. But I thought that, talking to Francois many years ago, that he was saying that's probably because of the convective adjustment you're using for your cloud convection scheme. Did I understand that correctly?
I discussed this problem of the moist stable state is really a spicy question, I guess, because there is definitely models with this stable state and other models without. And I discussed recently with a guy who used this model which find this most moist stable state, and the convective adjustment was the main candidate for to explain that. So yeah, the main possible answer is this convective adjustment, but there is also the problem of the quantity and the size of the nuclei in the atmosphere to form the clouds. So I have a few simulations ongoing with different density quantities of nuclei, but yeah, the preliminary results are not super incredible, and yeah, actually I guess this single problem of the moist greenhouse is an entire paper itself.
I would say it's many papers.
yeah. Yeah. And to go back on the beginning of your question about different kind of atmospheres, the main problem we have to model different atmospheres is that for each new atmosphere we have to create a new quality table, which is super time expensive and super long.
I'm well aware.
Yeah, so I wrote a piece of code to create new tables with CO2 mainly. So it will be possible for me in the next months, I guess, to test this for a CO2 dominated atmosphere. But right now I don't have enough data for that. But yeah.
Okay, great. Thank you so much.
Thank you.
We have also a question by Gavin Schmidt in the chat, so I'm going to read it. In the early transition, the tropopause moves up to the top of the resolved model. Is there a danger that the model results are going to be affected by that? Additionally, do you include all the effects of high water vapor on buoyancy, atmospheric mass, pressure gradients, etc.?
Okay, it's a good question. So actually, I had some problems because of this, because of the resolution of the model, basically. And when you put too much vapor at the top of the atmosphere or too much clouds, then there is numerical instabilities because the resolution of the model at the top of the atmosphere is not super great. But basically, if you increase the vertical resolution, then you don't have this problem, or this problem arise at higher temperature. But I didn't notice any strong modification of the results by increasing or decreasing the vertical resolution. So maybe at, for example, 400K, there is a little modification of the thermal emission because of that, but the general evolution of the atmosphere is not affected by that for sure. And second part of the question was buoyancy, right? Yeah. Yeah. Okay. So there is all these effects in the model. So I'm not an expert of these precise questions, but all of that is supposed to be included, and there is a rain in the model, and there is evaporation of the rain, and yeah. Sorry.
So I think a question also, yeah, do you include all the effects of high water vapor on buoyancy, atmospheric mass, pressure gradients, etc.?
Yes, I think so. I don't want to try to explain what there is in the model exactly, because I'm not expert enough of this question, but from what I know, yeah, there is all these adjustments for the convection, for the buoyancy and stuff like that in the model. So yeah.
Good. Thank you. Do we have any other questions? So I have one actually. So have you considered to eventually connect your GCM outputs with like a 1D photochemical model, so you can take into account the water photolysis that you will get, mostly in the upper part of the atmosphere, and that will affect the strength of your water line out there?
Yeah, it's definitely the one of the next steps, I guess, because I started to discuss with some people and to try to think about that, but I talk about stable post-runaway states, but from a climatic point of view, it's stable, but from the point of view of the evolution of the planet, it's not, because here these post-runaway states are at low, relatively low temperature, because we don't have a lot of water in the atmosphere. But if you add the Earth's ocean in the atmosphere, it's more than 200 bars, and you can reach temperatures for which you melt the surface of the planet. So if first point, you melt the surface, and at the top of the atmosphere you have a lot of vapor, and the atmosphere is super expanded, so you will have photodissociations and stuff like that. So these two problems, yeah, it's definitely, I really would like to study these two questions to see if how the planet will move in the parameter space when you reach the post-runaway state, because you have this competition between the top of the atmosphere, for which you destroy the water, and at the bottom of the atmosphere, if you melt the surface, then the interior will absorb a little bit of water. So but if you do that, you decrease the temperature, and I don't know how the planet will move in the parameter space, but it's definitely a good question, and yeah, I really would like to investigate these two processes.
Thank you. And I assume also your simulation probably run for a very, very long time, right? Specifically when you start to have an opaque atmosphere. So do you have a typical computational time for some of the simulation? And also when do you know you have to stop your model? Because when you don't aim for a convergence, or do you know that, okay, my simulation is done now?
So basically, for this evaporation phase, the time scale is about 130 years of simulation, which is in real time super long. That's a few months. And but for the last 10K, it's longer than for the entire beginning of the simulation, because of this strong augmentation of the thermal inertia of the atmosphere. And at maximum, I can evaporate 2.5 bar of water. And I stopped because then it's really too long. So that's why I tested only small amounts of water for the transition phase. And the time scale of this transition phase is actually pretty fast. It's if I remember correctly, it's about 40-50 years from 400K to 800.
Okay, that's good. Thank you. Any other questions? No? But as you know, I mean, I would put like my cuisine chef hats. I would love to have your 1D model in one of the cuisine MIP. I think it would be really great. And of course, the 3D model as well is already part of few of them, but it's super cool work. And yeah, I really like also the part when you showed at the beginning, you did there was some comparison between different models. Very important, I know, yeah.
Yeah, definitely. We can definitely discuss about that. Sure, I will be happy to help if I can.
Great, thank you. Okay, well, thank you very much again, Guillaume. It was a really great presentation. Yeah, it's been recorded, so if anyone wants to rewatch it, it will be online soon. And we will see you all in 2 weeks. We have a talk by Miles Curry. Thank you. Have a great one.
Thank you very much.
Thank you.